Thank you for turning up for this discussion. My name's Philip Ball, and I'm the chair for today. And we're going to be talking about whether change is needed to our fundamental understanding of the universe. Since the 1970s, we've understood the world through the lens of the Standard Model and its account of the forces and particles that make up the universe. The theory correctly predicted the discovery of quarks, force particles, and most recently, the Higgs boson. But a series of deep puzzles have emerged. The theory does not explain gravity, dark energy, or dark matter. And the quest for supersymmetry and a theory of everything to simplify the Standard Model's seemingly random complexity has failed. And now, even more significantly, evidence has emerged of a new force that is throwing the whole theory into question. So can the Standard Model be modified to answer the increasing number of challenges it faces, or is the Standard Model fatally flawed? And is it time for the next great paradigm shift to a radically different account of the universe? Alternatively, should we conclude that all theories have their limitations and not worry about the flaws, however profound they might be? So, to our speakers, Sam Henry is a renowned particle physicist working at the University of Oxford. He's authored several academic papers, as well as maintaining his own blog and running several science outreach programs. Sabine Hossenfelder is a theoretical physicist. She's also the author of Lost in Math, How Beauty Leads Physics Astray, which explores the concept of elegance in fundamental physics and cosmology. And virtually today we have Bjorn Ekeberg. He's an Oslo-based philosopher of science who researches the limits of scientific knowledge. And his book, Metaphysical Experiments, is a critical exploration of the historical foundations of physics and cosmology. So I'm going to begin by asking each of the three speakers to put across the case that they want to make in this discussion. To address this fundamental question that we're asking, is the Standard Model fatally flawed, and is it time for the next great paradigm shift? So first of all, I'm going to go to Sam too.
I do like the sound of a next great paradigm shift, because although particle physics is never dull, at the moment we'd really like to see a bit more excitement. It's been 12, 13 years since the Large Hadron Collider turned on, and we found the Higgs boson, and we then hoped that we'd see more discoveries, supersymmetric particles, dark matter, some sort of new physics beyond the Standard Model. But we haven't seen anything like that. In a way, the problem with the Standard Model is not that it's flawed, but that it's too good. Nearly every measurement that we've made has matched the Standard Model prediction perfectly. But we know that the Standard Model can't be the final theory because there are too many unanswered questions that are going to need some sort of new science to explain. So two of the big ones are dark matter and the matter-antimatter asymmetry. We know the majority of the mass of our galaxy can't be explained with known forms of matter. So there must be some new invisible particles out there, or else something else that we don't yet understand. The Standard Model predicts that particles and antiparticles are so symmetric that they should have just annihilated after the Big Bang, and the universe that we see shouldn't exist. So there must be some subtle asymmetry that we don't yet know that can explain why we're here. Since we know the Standard Model is incomplete, then we would expect to see some cracks forming by now, some measurements that don't quite match the theory. And that's why the muon G-2 result from this year was so interesting. The Fermilab laboratory in the US measured the G factor of the muon, a measure of the magnetism of this particle, and they showed that it didn't quite match the Standard Model prediction. So this could be a sign of something new, a new force we don't yet know. There never seems to be any shortage of theories of physics beyond the Standard Model. We used to be able to find lots of papers that were using these theories to predict papers just beyond the sensitivity of current experiments. We then built better experiments, did the measurements, we didn't see anything. So does this mean that these theories are wrong? Well, when you check the small print, it's a bit more complicated. There were assumptions made in these predictions, and if you change these assumptions, these particles could still exist, just heavier and harder to find. But it's now getting harder to find papers making clear predictions, and theories like supersymmetry that we were once told would be the next big thing in particle physics now seem to be terminally out of fashion. At this point, it'd be really great if something unexpected happened, if we saw something that nobody predicted, or if some radical new idea came along that would really shake up the field and make it exciting. But is that going to happen? Probably not. The less exciting interpretation is that we were just too optimistic about what we could see in the first 10 years of the Large Hadron Collider, and some variation of supersymmetry or another established theory is going to be correct, but seeing its effects is just going to need more data and maybe another generation of experiments to see that. But a great paradigm shift does sound like more fun.
Thank you, Sam. Sabine, do you think we just have to wait, or have we seen flaws in the standard model that reveal something deeper?
Well, I have to side with Sam that saying that the standard model is flawed is, a little bit too harsh a judgment, I would say, because we know it works perfectly fine. And indeed, that's kind of the problem. We would be happy if it turned out to be more obviously flawed, so to say. But we do certainly know that it has some shortcomings, though interestingly, I seem to see different shortcomings than you do. So dark matter, for example, it may be a particle, but maybe it's not a particle. So maybe it's not necessary to change the standard model at all. It may be something with our understanding of gravity. That's the problem. The mu G minus 2, yeah, it's kind of intriguing, but I mean, for one, it hasn't reached 5 sigma. That's the one thing. And the other thing is, as you certainly know, it's a hideously complicated calculation. It might very well be that there's just some problem with the prediction from the standard model, and that it doesn't actually hint that we have to look for new physics. But there are other problems with the standard model. One is what you already mentioned. It doesn't contain gravity. So we know that in some way we have to combine the standard model with gravity, because the particles in the standard model do gravitate. We know it, but we don't really know how it works. So that's certainly a big shortcoming. So we need a theory which is called quantum gravity, that no one really has any idea what it looks like. And the other peculiar thing about the standard model are the neutrinos. So the neutrinos, particle physicists, who work on accelerators usually don't talk about them much because they're somewhat hard to detect. But the neutrinos are really, really puzzling, because from all the other particles in the standard model, we have a left-handed and a right-handed version from the particles that have masses. But from the neutrinos, we've only ever seen the left-handed version. And that's a problem, because we need both the left and the right-handed versions to give masses to those particles. And we know they have masses. So how does this come about? We know for this reason that there's something missing in the standard model. Either there have to be right-handed neutrinos, which are just so heavy that we haven't seen them, or there's something weird with the neutrinos and they're just different to all the other particles in the standard model. And there's actually another anomaly, which was not on your introduction, in the LSMD mini-boon data, which looks for neutrino oscillations. That's a signal for neutrino masses. And that signal cannot be explained with the standard model. And it's actually now at 6 sigma, last time I looked. So that's really, really puzzling, and indicates to me very strongly that the standard model has to be completed. There are probably some particles that are missing. But, and here's the thing, you don't actually have to change the standard model all that much to add a few more particles. You can continue using the same mathematical framework, and I don't think it will really be a big paradigm shift. I think where the big paradigm shift is going to come from is another thing that particle physicists like to forget, is that the standard model deep down is based on a quantum field theory which brings in quantum mechanics and the entire measurement process. And how a measurement works in quantum mechanics is something that physicists never really understood. And so that's where I think the big paradigm shift is going to come from.
Thank you. Bjorn, we're going to turn to you. And this question, the way it's posed, is the standard model fatally flawed? You have made the point that actually we should be thinking about there being 2 standard models. There's a standard model of particle physics, but there's also a standard model of the way we think about cosmology, and that they're not the same thing. So over to you.
Yeah, thank you. So there is, in practice, these 2 overlapping spheres of standard models. We use a standard model also in cosmology, and not just in theoretical physics. And the standard model in cosmology is more built on the Big Bang theory with dark matter and dark energy and other building blocks on top of it. So since we're talking about the universe and making sense of the universe as the theme for the debate, I'd just like to point that out from the outset that I may be speaking to more of the problems I would see with the standard model in cosmology than in physics. And so from my point of view, having studied and followed this discourse for over a decade, the standard model of cosmology looks quite flawed, I would argue even deeply flawed. But you pose the question of whether it's fatally flawed. And so fatally flawed supposes the science will sort of die out the moment it's shown to be wrong or inconsistent in some way. And this is a very idealist notion. Instead, I would suggest it's actually possible in practice, and this is what's happening, is that the model can be flawed and it will keep persisting as the only operative model because it's the only one that's put to use. So in the sense, the point I would like to make is that the science, and here I'm talking about cosmology in particular, is kind of stuck. The paradox is that it relies on a theoretical framework that struggles to make sense of and fit some of these observations that we're making. But the model itself is so entrenched that very few cosmologists would want to seriously reconsider it. And reconsidering it is very hard work. So in a sense, physics and especially cosmology have become dependent or path dependent on the standard model, is how I view the situation. So it is in practice the one and only model, and some would claim that this is because it's right. Maybe more modestly, you could say it's because it's the best one we have. I'd like to argue instead that it's become too to fail. The reality is it would take enormous funding and work to develop an alternative theory that could explain all our observations better than a model that has been put to operative use for more than half a century. And without all that collective work, there will never really be a paradigm shift.
Okay, thank you, Bjorn. Well, maybe we'll get on to what such an alternative theory might look like later on. I think I want to start off the general discussion by thinking about where we are at the moment and how we got here, because one often hears talk about a crisis in physics, or at least in fundamental physics, in particle physics. And I wonder whether that's actually true, and if so, why is that the case? Why is it that we have this model that we know does a very good job of a lot of things, but we know that it can't be the final word, as I think you've all said, and yet we're struggling to make progress on that. It seems that it's proved incredibly difficult to find any hint of how we develop it, where we go from here. So why has the progress in these fundamental questions of physics why does it seem to have stalled recently? Sabine, if you could talk about that first of all.
Sure. Before I answer your question, though, for the benefit of the audience, I want to explain that we've now mixed together two different standard models. There's the standard model of particle physics, which I believe is what we were talking about. And what Bjorn was talking about is the standard model of cosmology, which is based on Einstein's theory of general relativity. That's kind of a different thing. It's more commonly called the concordance model or lambda CDM, so just you don't get confused. So yes, about your question, what's going on, why we're not making progress, I think it's a combination of two things. The one thing is, I guess that's the obvious thing to say, the easy things have been done like 100 years ago, and as a scientific discipline becomes more mature, it becomes more difficult to see new things, and so it just takes more time. But I also think that physicists have not been as careful in thinking about what they're doing as they should have been. So it's on the one side, there's a problem with theory development. After the completion of the standard model in the 1970s, physicists were really, really convinced that symmetries are great and you can use symmetries for everything. And this is why they constructed a whole new bunch of theories based on symmetry principles, grand unified theory, supersymmetry, as the name already says. And they looked for evidence for them and didn't find it. And now I think, that they tried it was all well and fine, but at some point they should have learned the lesson, because they tried it, it didn't work. But they never learned it. And so they just continue doing the same thing over and over and over again and build bigger and bigger detectors, and they keep not finding something new. So I think there's a self-reflection missing. And so these two problems kind of play into each other, because we have the theoreticians not being careful enough thinking about what might be the next prediction to look for. Then we build experiments that don't find anything, and so we just, continue to not make any progress.
Well, Sam, you're involved in some of those experiments, so what's your perspective on this question?
Yeah, well, first of all, I'd like to say that progress hasn't completely stalled. It's just not going as fast as we like, and maybe we're not seeing the kind of progress that we really want. But in experimental particle physics, we are doing things. 10 years ago, we didn't know the Higgs boson existed. We've now done precision measurements of its properties. Well, maybe not precision measurements, but measurements of its properties and of the particles it decays into, and we're using it as a tool to search for new particles. I guess also we're doing a lot of searches, and we're getting a lot of null results, searching for new particles and effects, but we don't see them. And null results are not as sexy as discoveries, but they're still an important part of the scientific progress. And let's not dismiss the effort of these teams. They're not going to win a Nobel Prize, but these students do deserve their PhDs. But I think, as Sabine said, it's true that we've now reached a point where I think there's a bit of a disconnect between the theory and the experiments. One of the problems is that the theory is so far ahead of the experiments, because by the time we reach a point where we've built a newer bit of apparatus, it now takes so long to build these accelerators, the theory has moved on. So we find the experiments we're doing were built, the design was chosen based on the theory 30 years ago, which is obviously not the best way to do things. And I don't really see an easy solution to this, because these experiments are now very difficult and they need huge collaborations to do it. Now, even the smallest particle physics experiments are several hundred scientists. And these collaborations, they take a lot of time to put together and to build the projects. Everything's getting more complicated, and the next upgrade of detectors at the Large Hadron Collider, we could be seeing 100 protons colliding at the same time. That leads to over 1,000 particle fragments flying out, and you have to keep track of every one to micrometer precision just to have a chance of identifying the signature as something new. So even the small sub-detectors of your component have teams of 100 people working on it. So yeah, it's going to be a lot more challenging, and I don't really have a solution to this. I think maybe we do need to rethink about the connection between experimental physics and theoretical physics.
Well, that touches, Bjorn, on the issue that you raised about path dependence, because what Sam has said is that purely by the nature of this big science that is involved, one has to commit almost to a theoretical position, perhaps decades in advance of having the experiments to test it. Is there, from the point of view of a philosopher of science, is there a problem in that way of doing science?
Well, there is a general problem for the development of the sciences, of physics and cosmology. That's as part of the historical picture, is that it comes up against certain limits. So there are fundamental limits. The history of science is this amazing trajectory of how we are able to measure and expand our knowledge within the universe. But there are fundamental limits that are always, that the history is about surpassing. And I think what both Sabine and Sam are pointing to is that progress seemingly stalls, because we have this idealist notion of progress from a century ago, and it's harder and harder to get further into nature, whether we're looking in the microphysical scale or further out into the universe. So in this perspective too, I want to point out that the situation in cosmology is a little bit different from particle physics. In that, like physics in the microscale, you can do experiments under controlled conditions, as Sam is pointing out. In the macrophysical universe as we know it, we can't do repeated experiments the same way. And we're talking about a scale here that is 20 orders of magnitude higher than the scale of particle physics. So this leads to certain kinds of problems just with basically how confident we can be in our own measurements about the scale itself, and so on. So I think it's important to keep in mind that with this subject matter, whether we are looking inwards to the inner part of particle physics or outward in the universe, is we are also fumbling. In a way, we are fumbling in the dark. And we're using a map which we are very afraid to let go of, because if we tried to replace the map, we would risk being lost altogether. And that is a very precarious situation. I mean, this is part of my interest in cosmology and in theoretical physics, is that it just exists at this limit of what is knowable. And I believe this is what also Sam and Sabine find exciting about this kind of work. But yes, it is. There are some fundamental problems here.
I mean, it sounds as though perhaps some of the problem is that the understanding of this area is advancing on these two fronts that are quite, in some ways, quite distinct. That, as you say, you can turn a telescope onto a certain object in the sky and make an observation tomorrow. And as we have found, those sorts of observations can fundamentally change the challenges that theorists and perhaps even experimentalists have to face. So, no one was necessarily, I mean, we've known about dark energy, we've known about dark matter for some time now, but, that came out of observations rather than any theoretical motivation. Dark energy came as a surprise back in the 1990s, but, it's confronted high-energy physicists with a new problem, a quite deep fundamental problem that wasn't originally on their agenda, I guess. I mean, does that create problems that actually astrophysicists and cosmologists can create problems for you overnight, whereas you've already sort of launched on a particular program of experimentation?
I think that's certainly true. That can be a problem. And maybe the problem is that one field of physics is often looking to another field of physics to solve their problems. So the astronomers are all convinced that dark matter exists, and they're just waiting for us to find it. But of course, as Sabine has said, there's many possible ways of solving the dark matter problem. And, new particles are one way, but there are also theories of new physics and new gravity, modifications to gravity. And it seems, I can't keep track of all of the developments in theory. It seems that these things go in and out of fashion. At one time, everyone thought it was particle dark matter. Now it seems that modified Newtonian dynamics might be coming back into fashion. But I think, the astronomers, they don't, they just seem to say, right, dark matter exists, we've shown it, you go find it.
Right. Okay. There's more we could say about that, but I want to move on to the next topic that we want to, which I think follows on quite naturally from that issue, which is really to ask how serious this problem is. You said, Sam, that perhaps we were too optimistic in what the Large Hadron Collider would find. And so far it hasn't found, for example, any clear evidence of the idea of supersymmetry, which people were certainly hoping was going to be the next step forward. So, and now we have the muon G-2 results that you say, suggest that there may be something that we don't really understand. How serious are those problems? And in particular with supersymmetry, I mean, is it causing panic amongst, amongst theorists that there is no sign of it? Or did they expect this to be an extremely hard thing to detect?
Well, maybe to first mention the anomaly we've seen, which is the muon G-2 thing. I mean, what this is showing us is that there's something that's interacting with the muon that's not in the standard model. And the muon is a great particle to study because it's heavy enough to be sensitive to new physics, but it also lives long enough that you can actually put it in beams and storage rings and actually study it properly. And so there seems to be something that's either interacting with the muon, or it could be interacting with something that's interacting with something that's interacting with the muon. It could be a second or higher order effect. And this could be a new force, but really we don't know how it's best to describe it. It could be a new particle interacting via an existing force or some variation of an existing force. And the muon G-2 experiment is a brilliant probe for searching for new physics because it depends on so many things. But this also means that having observed it, we don't really know what it means. There's so many possible theories that could explain it. Supersymmetry was one, but then supersymmetry hasn't been seen at the Large Hadron Collider, so maybe we need to look at other theories. And when you look at these other theories, what does it tell us? Well, we know that the vanilla flavor of supersymmetry seems to be out, but maybe some alternative version of supersymmetry could still be correct. But there seem to be no shortage of other theories: Kaluza-Klein particles, extra dimensions, Z primes, leptoquarks, technicolor baryons. There's so many theories that, as an experimentalist focusing on the hardware, I can't keep up with them all. So I just have to listen to people like Sabine to tell me which ones I should be paying attention to.
Well, I was very struck by that how as soon as this result came out, the physics community in the preprint server where physicists post their papers were flooded with theoretical explanations. So many that you kind of have to wonder how constrained at all is this problem if so many theoretical explanations for something quite new can seemingly be cooked up almost overnight. Sabine, maybe you can talk to that issue. Do we really know what the problem is? Or, is there too much room for maneuver?
Yeah, so that's an excellent point. Though I have to say, as it's often the case, if there's a new result coming out, there are a lot of people who already know it's coming. Mm-hmm. So they may not have written the papers overnight, and they had some advance warning. But it's certainly true, and that's exactly what I mean when I say we have a problem with theory development. When you can explain everything by your theoretical methods, then since you were asking, you shouldn't pay any attention to those predictions. They're entirely worthless. And that's what we see. That's why they're being ruled out over and over and over again. Because you have all these theorists, they literally guess their models because they like one particular particle or they like one particular symmetry, or they get obsessed with, some anomaly in astrophysics that's currently on vogue, and then the next year it's gone, and so on and so forth. And it just leads nowhere. And I really think that theoretical physicists, they have to have a hard look at their methods of theory development and throw out what didn't work. But the problem is exactly what Bjorn said. We have this path dependence. And so we have settled on a particular method of making new predictions, if you want to call it that way, for new particles, which you can then rule out. And that works very easily if you've learned how to do it. Like, this is what I was trying to do. Basically, I know how it works. And that's how you can write papers. And that's how you get grants. And that's how you get your students. And then the students become professors. So it just goes on and on like this. And if you want to do something fundamentally new, you'll have to start over again from scratch, and it becomes very, very hard to find any support.
One alternative to that is, and this seems to be the one that's in the air at the moment, we need a bigger machine to find out more. You've expressed some skepticism about that, whether that's the right way, Sabine.
Yeah, for exactly this reason. We do know, as I think we all agree, that the standard model has some shortcomings and there has to be more to it. But there's no reason why building a bigger machine would give us any help in developing that underlying new theory. All of those anomalies at various levels of statistical significance, they may be resolved at much, much higher energy. So even if we build this bigger collider, which they are planning for at CERN, and it would have a circumference of, I think, 100 kilometers and cost something like 20 billion, not counting the operation cost, which would be another 20 billion or something. So we're talking about a huge bunch of money. And the outcome may just be, well, the standard model works just fine. And I think that's a little too much money for that little prospective payoff, which is why I think we have to figure out what are more promising experiments to look at, where we can expect a bigger bang for the buck, so to speak.
And Bjorn, it occurs to me that this is somewhere where the philosophy of science might actually be helpful, and it's been interesting to me that there seems to be more dialogue now between high-energy physicists, fundamental physicists, and philosophers of science to try to find some resolution to this problem. And one of the issues, as you've touched on, is how you know when you just keep waiting because you have a theory that seems to do a lot of things pretty well, and so you don't want to throw it out, too casually. And when you actually decide, no, hang on a minute, we need to turn back, we need to go back down the path and rethink some of the fundamentals. Is there any guidance that the philosophy of science can give to that question?
Well, I am also positive about, I'm seeing increasing dialogue in these fields. When it comes to the nature of evidence, for example, this is where it's worth noting that we're talking here in the context, for example, of dark matter or these latest experiments. Something like evidence is often bandied about, and there's a sense in the field that something has more or less been proven. Something like dark matter is taken by a lot in the scientific community and beyond as just more or less proven to exist. And it's worth pointing out that how the evidence for something like dark matter comes about is not in any direct empirical sense. In fact, there is no direct evidence of dark matter at all. It is an inference from the discrepancy that happens between the theoretical model prediction and the observations we make. So the basic assumption underneath a lot of this is that if the model that we're using is correct, there has to be something like dark matter or a new force or something to explain that gap. This is a familiar pattern in the history of physics, and this is especially true, I think, in cosmology, that the more observations we make, the more discrepancies we find with model predictions, the more cosmologists adjust or add parameters to fit observations, or they propose additional hypotheses or new physics, or such as a new force, and or like in the case of this latest experiment, which is all very exciting for scientists because this means a path for more research. But it's just worth pointing out that what a lot of these kinds of solutions have in common is they also preserve the core assumptions. They add on something or erase a new question, but they make the more fundamental or radical questions almost impossible to reach. And so I think the philosophical view, I mean, it's very limited. I'm not in a position to judge the merit of particular kinds of evidence, but if there could be any help in asking more fundamental questions about how we got into this situation in the first place, might be helpful.
Right. Sam, I'm also wondering whether is just a bigger machine the only alternative, the only empirical alternative we have for addressing these problems? I mean, we talked a little bit just beforehand about, ongoing work on the mu on G-2 issue using the devices we have already. Are there other ways that we can already be seeking for a path forward without having to build this even bigger collider?
Well, I think that this is an open question in particle physics at the moment. And there certainly is this plans for a future circular collider. But I think it's there's no means agreement among particle physicists about whether this is the right way forwards, for the reasons that Sabine has said, that, it may well be that we build such a machine and it doesn't actually find anything. And, of course, that's very difficult to predict, but we do want to focus on the experiments that are most likely to deliver an interesting result. The alternatives, it could be that, more precision measurements of particle properties could be interesting. Things like the mu on G-2 experiment, also measurements of the electric dipole moments of particles. This is another way of doing particle physics, but there's only so many of these experiments that we see at the moment. I mean, other possibilities are maybe do we need to look at ways of studying the ultra-high energy cosmic rays that are bombarding the Earth from outer space at energies far higher than anything we could ever reach with an accelerator we build? Or do we want to study neutrinos, which are a completely different game to studying other particles? So there's all sorts of different experiments that we could be doing in the future. And yes, this is an open question in the field at the moment, is what direction do we want to go in? And maybe I think what we'd really hope is that, if we discover some particles at the LHC and that suggests that there's going to be more a little bit further, then that would build on the case for building a bigger accelerator. If we don't discover anything, then I think it's quite likely that people are going to listen to theorists like Sabine and say, actually, no, this is not the right way to go. But then there will also be other people who will say, well, we still need to explore further. So, there is a case for building such a machine anyway, because, we just need to explore to higher energy scales. And if we stop now, we'll never go further. Even if a new machine doesn't see anything, it would be at least a technology demonstrator for the one that may come after it. But I think that's going to be a very hard argument to convince somebody to spend 20 billion on such a project.
Right. I wonder, before we move on, I'd like to just say a little bit more about the dark matter problem, because although it's not the only, clearly not the only puzzle facing fundamental physics, it's probably one of the ones that people hear most about and know most about. Here there have been many searches for dark matter particles that have still found nothing. Sabine, do you think that we just, in that particular case, we just need to keep looking, or is there something else we should be doing to try to resolve this issue of why we seem confronted with a need for dark matter?
Well, as Bjorn said, the evidence that we have for dark matter is indirect. So we infer that there has to be, if you believe that it's some kind of matter, we infer it from astrophysical observation, gravitational lensing, for example, or galactic rotation curves, motions of clusters. We measure their velocity, and we just know that it doesn't work with general relativity and the standard model. If you combine it, it doesn't come out right. And adding a new type of matter is the easiest way to resolve this discrepancy between the observation and the theoretical predictions. But these observations are very unspecific about what exactly the properties of this dark matter are, if it exists. So we don't really know what's the mass of the particle. We don't know how it interacts with itself or with other matter. I mean, we do know that it doesn't interact with light, because that's why it's called dark, but that's pretty much it. And so if you know that little about a particle, it's really, really hard to build a detector for it, because you don't even know what you're looking for. And so the reason we've built a particular series of detectors, actually there are kind of two types of experiments. One type is looking for a type of particle that's called a WIMP, a weakly interacting massive particle, and the other one is an axion. And both of these particle types, so they're actually classes of particles, you could say, were motivated by theoretical arguments. And that brings us back to the problem with the theory development, because you can ask how well motivated were they actually? So WIMPs in particular were very popular because they come out of supersymmetry. So it brings us back to what I said in the very beginning about how particle physicists came to like symmetries. And the axions, they were predicted basically to, make the standard model a little bit prettier. And the original version of the axion actually was ruled out very, very quickly in the 1970s. And what happened afterwards is that physicists just made the theory more complicated. This is something, by the way, which we see over and over and over again. Bjorn already mentioned this, that if you have some prediction that runs into conflict with the experiment, then the theorists just go and make the theory more complicated. So in the end, it can just accommodate everything. And that's also what happened with the axion. And that's what happens now when every time these dark matter experiments don't see the particle that they were looking for, the theorists will just go, oh, it's a little bit more massive, it's a little bit less strongly interacting, and we'll have to build a bigger detector.
Okay, well, finally, I want to ask, why does it matter? Why should we care? And it's lovely to see that, presumably for all of you, you do care enough, at least, to come and hear about it. But really, the question is, if we discovered, Bjorn, for example, if we discovered that you're right in thinking we actually need to go right back and really fundamentally think about and perhaps change some of the assumptions that have brought us to this point so far in terms of the standard model or the standard models, would that have had wider implications, philosophical and social? And I'm thinking here, that clearly in the past, changes in our cosmological worldview have done. The heliocentric theory did seem ultimately to have broader implications. The discovery of the Big Bang, arguably changed our view of where we sit and what our role is, if you like, in the universe. Do you think that there is the potential here, at least, for that kind of fundamental rethinking of our position that reaches beyond questions that are, really only of interest to specialists?
Well, I think I've tried to make clear from the outset that my own view on this is a little bit skeptical of how major changes can come about. But to the question of whether it matters and how it matters, this of course does depend on what we would change it to, what a change would look like, or how radical it is. As Sabine just described, the standard model of cosmology that I've been looking at the structure of is like a series of building blocks on top of each other. It's a very, very complicated multi-layered theory. It looks, when you map it out, like Jenga, if you're familiar with this game, where it's like multiple blocks that sit on top of each other. And if any of the blocks underneath fail, some of the other ones will fall, or you can replace one and put another one. Dark matter is such a block somewhere in the middle of that structure that there is another contender for, which I know Sabine is working a lot with as well, modified Newtonian gravity, or MOND in short. So to put this in perspective, if what we call a paradigm shift is, for example, that dark matter becomes more or less abandoned and in favor, like that we move in favor of modified Newtonian dynamics, if that were to overtake something, I doubt that it would affect many lives outside of the scientific community. It's like replacing one block with another. But if we are talking about a new understanding of light, or new understanding of gravity, electromagnetism, or other forces, or even if we are questioning and talking about the origin story that the universe began in a hot and dense state, a paradigm shift like that would, of course, have like enormous cultural impact. And I think the point I would like to make is that our understanding, since we're talking about how we understand our universe, understanding relies on explanation. And the power of a theory traditionally lies in its power to explain something. And when you look at the field of physics and cosmology, the way it's developed over the last century, historically speaking, it's become better and better at describing phenomena with more precision and detail and layers, but it's also become poor at explaining them. And I think this is part of the problem, that there's a lot of people inside and outside the scientific community are finding the current paradigm wanting for something. Like, it doesn't explain very much, for example, if MOND becomes the favored theory over dark matter. What does it mean, for example, that the implication that gravity is variable at large distances, which is what MOND presupposes, that our laws of gravity as we know them in our own galaxies don't actually translate further. What is the implication of that? That is, I suppose these are the kinds of questions we can get to, but I am not sure if this alone warrants a major paradigm shift in the context that you're discussing here.
Sam, I wonder about these issues from your point of view as someone who's working on these experiments that happen, of course, in vast international teams, trying to look for things that are very, very hard to see, and probably, making incremental progress in doing so. Is there sort of behind that quest, is there in you and your colleagues a sense that actually you might find something that really profoundly upends our understanding of the way things work? Is that part of the motivation?
Well, I think that's not something we really expect to find, because I guess everything we do is always building on everything that's happened over the last 20 or 30 years. And so any changes that we expect to see can probably be explained by just introducing another particle into the standard model. But I suppose we always live in hope that we're going to see something really unexpected. And I guess maybe one way we can imagine what might happen is let's think back to a great paradigm shift that never was. And that's 10 years ago, when for a short period, the Opera experiments convinced everyone that they just might have seen neutrinos traveling faster than the speed of light. And nobody believed it, because it was very difficult to fit in with our existing framework. But the idea was just so exciting that for a short period, it was all people could talk about. And how could we possibly, rewrite the laws of physics to accommodate that? And everyone got really excited about it. And that was not just in the particle physics community, it also got a lot of media attention. The idea that, particle traveling faster than the speed of light got a lot of attention. And so for a brief period, it was really exciting. And then, of course, it was a rather sad end that it turned out to be a faulty electronic module and an optical fiber not properly plugged in. But I think that at least gives us some sort of idea of the kind of excitement we'd see if there was some sort of unexpected result that did point at that we need to completely rewrite our whole framework.
Sabine, I get the impression from you that sometimes part of the motivation you have for thinking about these things, and it seemed to be what you were sort of saying in Lost in Math, is that you want to challenge the way that, it might be too broad to say the way science is done, but there are some things about the way this science is done that you feel could be done better or differently. Can you say something about that?
Yeah, exactly. So the Opera anomaly, by the way, was another example where theoreticians were very, very quick to find all kinds of explanations. Which drives home the point that it's fairly easy with the current methods that are currently accepted to explain pretty much everything. And so we talk about the scientific method as if it was a fixed thing, but it's a living and evolving thing. And what counts as good science at one point in the history might no longer count as good science 100 years later. And I think that in the foundations of physics, we have to ask, do we need to update our methods? And for me, the answer is clearly yes, we have to. We have to be more careful in our theory development, more careful to write down what the assumptions are and to ask whether they are justified. So, for example, this conversation we're having here, I think it's great that we're having it, but I think that there should be more physicists having this discussion. But maybe if I can say something about your question of does it even matter, which is kind of, if you ask this question among physicists, it's kind of blasphemy. It's a question you're not even supposed to ask. But I think you have to be more careful about adding, does it matter for whom and when? So it clearly matters for particle physicists. If we don't build a bigger particle collider, that matters to them. But does it matter to society? If we find a crack in the standard model, if we find a new particle, that kind of thing. And that depends very strongly on exactly what it is. So as I said earlier, physics is a very mature discipline, and the easy things have been done. This also means if we find something new, it's very unlikely to have an immediate impact on daily life, just because if it's difficult to measure, it's probably also difficult to use. So if we find some particle that makes up dark matter, I can't really see what difference it would make for daily life. But there may be some consequences in the future. You just discard Mond as something that would never be of use to anybody. But I don't know. If one day our civilization manages space travel, maybe we should know how gravity works.
Mm-hmm. Well, can you please join me in thanking our panelists today, and thank you all for coming too.